So in today's class we are just going to start with the power sources. We are going to slightly understand little bit more
Sir,
about what are the various kinds of power
sir,
sources. Yeah, tell me.
sir, are you recording?
Yeah, I am recording it.
Okay,
Okay,
okay.
I am recording it. Okay. What are the various kinds of power sources which are used in an electrical system, right? Okay. So generally, theoretically, there is something known as an ideal power source, but you won't find those ideal power sources in practical circuits, right? So what is an ideal voltage source? So if I define an ideal voltage source, it means there is no internal resistance, and it can supply infinite amount of current, keeping the output voltage at the same level. That means suppose I have an 12 volt battery. If I connect an 12 ohms resistance, the voltage across the resistance will be 12 volt, and the current will be 1 ampere. And if I am going to connect an 12 ohms load, then it should provide me 1000 amps of current while maintaining the same voltage, right? So these kind of circuits we do for theoretical calculations. We use these kind of sources in circuits, but in practical applications you will not find an voltage source which is like this. Okay, so in practical voltage sources you will always have an resistance in series with an voltage source. So where does this series resistance come in from? Because suppose I take the case of an battery, then the plates and the electrolyte, okay, they are not perfect conductors, because the current has to flow not only in the from the positive terminal to the load and come back to the negative terminal. For the current to flow, the current also has to flow from the negative plate of the battery to the positive plate of the battery through the electrolyte, right? So the plates also offer some resistance, and the electrolyte also offers some resistance. So there is that is the reason you those resistances will be lumped together, and it will be called as an source resistance, which is in series with the resistance. Similarly, if you have a generator, right? Generator is generally made up of inductors, coils, where a magnet is moved, and due to magnetic induction some voltage will be induced in these coils, an inductor. But you can't have an inductor in practice which has got zero resistance, because after all it's a copper wire, right? So it will have a finite resistance. Okay, so if it's a pure inductor where you have only L value, then it is an ideal inductor. Whereas practically whenever you have a coil, inductor coil, you will have some resistance because of the copper winding, so a series resistance will come. So what is the limitation which happens due to this resistance Rs in series? Suppose you are connecting, say it is a 1 ohm series resistance. If you are connecting a 1 k load resistance out here, so that 1 ohm is particularly almost negligible compared to 1 kilo ohm. So it will not have an worthwhile effect, and a very negligible effect it will have. You will get almost the whole voltage available across the terminal. Suppose I have a low load resistance, say suppose I have 1 ohm here, and I'm connecting a 1 ohm load. So if you see the what is the terminal voltage, it gets divided by half, right? Because the current is going to flow through this source resistance also. So there will be an IR drop across this resistance also. So in effect, in all practical voltage sources, there will be a series resistance along with the voltage source, and when current flows in this series resistance, the output voltage which is available for us across the load will decrease. The more current we are drawing from the source, there will be a more drop across the RS resistance, that is the source resistance, and the terminal voltage will drop. So that is the difference between an ideal voltage source and an practical voltage source. Also, all practical source cannot provide current, infinite current. So there will be after certain value, the capacity of the practical source to provide current stops. Okay, beyond a certain limit it won't be able to provide current. Like here, if you have a 10 volt source and you are going to connect a few nano ohms load, it will it has to provide current, right, for an ideal current source. So while doing calculations, you will just use the V equal to IR ohms law, without taking into consideration that there is a limitation on the current. Whereas when we do an actual implementation of a circuit, that may not be possible, that this source may not be able to provide that kind of current. Okay, so these are the differences between an ideal source and an practical voltage source, right? Okay, so these are the battery, and then you connect a voltmeter out here. Now voltmeter, generally it has an huge resistance in series. So if you see here, this is 1.5 volt and 1 ohm. If you try to measure the output voltage out here, so you will get close to 1.5 volts, because this voltmeter is a high impedance device. So when this is 1 ohms and this is 10 mega ohms, so you will get the total voltage available. Whereas if you are trying to connect a low load across the battery, say in this example 8 ohms, then the total voltage available across the 8 ohms will be only 1.33 volt. Okay, because some current will flow here and there will be a voltage drop across the resistance, okay, which is not negligible, because now 8 ohms is comparable to 1 ohm. So you will find, so these are some of the standard cells what we have, and the internal resistance of those cells. Okay, if you see, 9 volt lithium battery has got 16 to 18 ohms internal resistance, right? So alkaline batteries have got much lesser, right? So nickel cadmium batteries have got very so they are much more stable devices. So these are various kinds of batteries which are available. You don't have to remember these values. Okay, so for the exam point of view, don't try to mug up all these things. In exams you will generally have to analyze circuits, so you don't have to mug up anything. Just understand the concepts, that's all. Okay, so this is what now many a times you have regulators employed in circuits, like you have if you have a bike or a car or something, right? So initially you will have a battery, but then once you start your engine, you will have an generator or a DC generator, which takes the drive from the engine and develops the DC voltage. So now that the engine RPM can fluctuate, right? So once the DC RPM fluctuate, you can't have the output voltage also to fluctuate, right? So you use regulators. Okay, these are known as regulators. So these are 7805 regulators, which are generally commonly available in the market, and it is widely used. Okay, so what does 7805 means? The 78 series ICs, these are all known as 780 series ICs. 05 indicates the output voltage will be 5 volt. Okay, so now if you see 7805, you need to give an input voltage more than 7. Okay, and it can vary from 7 to around 14-15, no problem, but the output you will get as a fixed 5 volts. Okay, it will remain as fixed and 5 volts. Okay, so this is the internal circuit diagram of this IC. So again, there is no need for you right now to understand all these things. I am just giving a overview of water. So why I want to I introduced this topic to you is, okay, suppose we have something like this in our circuit. Okay, will it have an internal resistance? Anybody?
Yes, sir.
Yeah, you can assume, if you have a regulated supply like this, that then you can assume that it has got a zero input resistance, series resistance, right? Because if you see, effectively this terminal voltage remains 5 volts irrespective of the load what you are current you are drawing from this. Okay, It can give a maximum current of, see the ratings you will see, the I out is 1.5 amperes. So from 0 to 1.5 amperes, it will give a constant voltage of 5 volts output out here. So for these kind of ICs, you can assume that the series internal resistance is 0, because you have a regulated output. Okay, so is it understood? Anybody? Is there any doubts? It is, I'm just telling you, giving you an overview. So when we generally, so if you go for an interview, if somebody says, okay, yes, you have does all DC sources have series resistance, right? So the answer should be no. In case you have an regulated power supply, then you can assume that the series resistance is 0, because as the load current increases, internally a feedback network ensures that the output voltage remains constant and it doesn't fall. So you don't have this IR drop here in this voltage regulator within this side. So that is the reason you can consider this to have an 0 input resistance. Is it okay? Okay. So similarly, you will have function generators like this, which can give a DC output voltage. So this also it has gotten, it can give up to 50 milliamperes of current, but this voltage will remain constant irrespective of your load what you connect to it. Okay, so that is the reason you can assume that these kind of sources have got 0 series resistance. Okay, so this is what you need to know about this. Okay. This is one the same thing, current source, practical current source. So a theoretical an ideal current source would be something like this, and irrespective of what load you connect, okay, the current will be same, right? So this is going to be an suppose it's an 1 ampere current source. Okay, if I connect a 1 ohms load out here, what will be the terminal voltage? Anybody? It's a 1 ampere.
IR.
Yeah, IR, that is 1 volt. Okay, now suppose I connect an 1 mega ohm resistance out here. What should be the terminal voltage? It will go to IR, right? 1 mega ohm. So 1 megavolt output voltage should be available here. So you understand, these things are not physically possible to realize such circuits, right? Ideal current source, you have an 1 ampere current source. If you are going to put an 1 mega ohm resistance, then to ensure that 1 ampere flows into that 1 mega ohms resistance, this current source has to generate 1 megavolt terminal voltage. Okay, that is not possible, right? So that is not possible. So these are all ideal current sources. For our theoretical calculations, within there we will use these values, but practically you have to understand. Okay, so this is, so that is why you have an non-ideal sources. These are known as the practical, all practical current sources will have an resistance in parallel to it. Now if you connect a very large resistance, okay, most of the current will go into the internal parallel resistance, and then you will not have that kind of output voltage. So if you see out here, this is the current and this is the voltage. So as you keep increasing the load resistance value, the output terminal voltage comes down. In this case, it's saying that no, the current is remaining same, but that doesn't happen in a practical current source. Okay, so you will have to understand this difference between an ideal and practical current source. Okay, now this is the classification of power sources. So electrical sources can be classified into independent sources and dependent sources. So independent sources, we have just now discussed what is a current source and a voltage source. There is something known as a dependent source also. So there are again 4 types of dependent source. One is known as the current controlled current source. That means essentially it's a current source, but the value of the current depends on value of the current in some other portion of the circuit. Okay, so similarly current controlled voltage source, that means there is a voltage source available. This is a voltage source, but what is the output voltage? That depends on the current in the circuit, okay, in some branch of the circuit, or current in some element of the circuit. Okay, so these can be this not theoretical things, these are practically implementable. We'll see that in some of the examples. Similarly, you have voltage controlled voltage source. That means it's a voltage source whose output voltage depends on some other voltage in the circuit. Similarly, you have voltage controlled current source. It's a current source whose current output depends on voltage in some other portion of the circuit. Okay, so these are the four kind of dependent sources which is available, right? So independent sources, these are the symbols which we use. This is for an DC voltage source, this is for an battery, and this is for an AC voltage source. So the thing to note out here is the terminal voltage is completely independent of the current through it, because these are all ideal sources. Okay, so whenever we just represent the source only by these symbols, it is assumed they are ideal, and the terminal voltage is independent of the current through it. That means there is no series resistance out here, and it can provide infinite current. So whenever you are solving problems, and if you have these kind of sources in the circuit, then it is assumed that the current could be of any value, but the terminal voltage will remain whatever is specified. Okay. Similarly, so this is what. So here only thing is that the third symbol has been changed. So in case you are using a DC generator, this is the symbol which we generally use. Okay, now if you see here, this is the current. So as long as the current is positive, that is the current is coming out from the positive terminal, going into the circuit and coming into the negative terminal, then we assume that this source is delivering power. Okay, whenever there is a current in the reverse direction, that is the current is emitting from the negative terminal and getting into the positive terminal, then that it means that the power is being absorbed. Okay, that can happen, right? So because if you have a battery, and say if you have a generator which are connected, so generator can charge the battery, right? So even in practical circuits, right, you use the generators to charge the battery. So you will have or you have the chargers to charge the battery. So it is possible that the current can flow into the source, and the current will be negative. Okay, so in that case we call it that the source is absorbing the power. Okay. So this is the same thing with the current sources. If you see an ideal current source, if the current is coming out from the current source and from the positive terminal, it is delivering power. But there could be a situation in the circuit where the current could be negative. That is, the current is going into the current source, and then we say it is absorbing the power. And whenever a source is delivering power, we call the power to be V into I, which, and we give it a positive sign for it. Whereas if the current is going into the source, then V into I, we take it as minus I, and the total power we have it as a negative power. Okay, a negative power only indicates that the source is absorbing power, right? So these are the dependent sources. So you have an circuit like this. Now if you see here, you have an source, current controlled voltage source, that is, it is going to generate a voltage which depends on the current in this circuit. Okay, now looking at this, this is a small symbol put like this here, but you could have an actually this thing can be implemented, right? You can implement it. Suppose I put, say, one milli ohm resistor in series out here, right? So it will so if I take the voltage across that, okay, it will be proportional to the current which is flowing in this circuit, right? And that 1 milliohms will not make much difference out here. So that 1 millivolt, if I put an amplifier and then I output of the amplifier I put it here, then this voltage will become, right, proportional to the current which is flowing out here, right? So those kind of circuits, and although in symbol it is shown out here like this, but this itself will be a small circuit, and it is physically can be realized. Okay, there is no problem in that. So there are these are the symbols, like this is an current controlled current source. Okay, now if you see, the proportionality constant will be K, because this current is proportional to another current. So obviously this will not have any it will not have any unit, so it is just KIX. Similarly, you can have a current source which is depending on a voltage Vx in the circuit, in some other circuit, in some other branch of the circuit. So this will be the one which is going to have the G. It will be called G as a transconductance, so that once you multiply transconductance with V, it will give current, right? So G, transconductance, stands for I by V. Okay, so that's why we use the symbol G. Similarly, you can have an voltage controlled voltage source. Again, the proportionality will be K, because voltage to voltage conversion. Or you can have voltage to current conversion. In that, this proportionality will be R, which is the resistance. So we are converting V to I, so you will have to multiply it with R. Okay, so these are the various kind of symbols which we use in the for dependent sources, right? Okay, now these are some of the simple concepts of power supply sources. If you have voltage series sources, you can connect them in series, right? So if you see here, the third source is connected in the opposite direction. So the output voltage available from that will be algebraic sum of the voltages. So in this case, V1 and V2 will get added and V3 will get subtracted. So this is the equivalent. So these three sources can be shown as a single source with an voltage V1 plus V2 minus V3. Okay. This is how. Similarly, you can have current sources. Current sources can be connected in parallel. So the net current we can represent these three current sources using a single current source, and again the currents will be algebraic sum of these currents. Okay, so I1, since I2 is in the reverse direction, it's a negative out here. I3 is again in the positive. Okay, so these are the two kind of transformations we do to simplify the circuit when we solve circuits. Is it okay till here? Okay.
Yes, sir.
Yes, sir.
Okay, good. So we move forward. So there is an possibility that there is a requirement of connecting two voltage sources in parallel. So the one of the conditions is, when we connect two ideal sources in parallel, the output terminals should be same. Right? If they are not the same, you cannot do that. Okay, you can't solve these kind of problems. So these are ideal sources. You can't connect two ideal sources with different voltages parallelly, but you can connect them in series. Okay, so is there a requirement to connect them in series? What is the advantage in connecting two of these sources in series? Anybody?
Sir, there won't be any advantage in series.
There won't be any advantage.
Sir, resistance will increase.
uh, Resistance will
Sir, we'll get more voltage source.
more voltage. Yeah, you are all somewhere there. You can be more specific. Think over.
Excuse me, sir.
Yeah, tell me.
Sir, my internet connection was a bit low. I wasn't able to understand what you said from this page, the series and parallel connection of sources. Can you please repeat it?
This one. Yeah. Okay. So I'm telling. See, when we have two ideal sources, we can connect them in parallel, provided the voltages are same. In case the two ideal sources with different voltages like V1 and V2, it is not permitted to connect them in parallel, because when you are computing it, what is the voltage will you take? They are ideal sources. They are supposed to maintain the terminal voltage irrespective of the load condition. So this is not possible. Physically, you can't have this kind of situation. You can only have V1 equal to V2, then you can have two voltage sources which are connected in parallel. So now my next question was, now why at all we have to do this? Is there any advantage in having these two voltage sources connected in parallel?
Sir, if one voltage source dies out, the other still keeps working.
Yeah, okay, let's come to the death aspect later, but when they are living, then they're still alive. Then what happens? Then if you see the total
So total internal resistance is reduced.
yeah, yeah. I can put it like this, that the current which will be provided by these two sources will be half. Correct?
Yes, sir.
Yeah, correct. If say I have two generators which are running, each can produce say 100 amps of current. Okay, that is the maximum capacity. But if I have loads which are more than 100, so I can connect two generators running in parallel. Correct? Isn't it? Similarly, I have two batteries if they are connected in parallel, right? So the current which will be drawn from each of them will be half. So I can increase the life of the batteries. Suppose I have an inverter at home, I have a single battery, it has got certain capacity. If I put one more parallel battery to it, so the amount of current which will be drained from each of them will be only half if I have put two batteries in parallel. Correct?
Yes, sir.
Yeah, so that is the advantage. Okay, now if you see in all practical circuits, it is not that we don't connect different sources of different voltages in parallel. Say you have a generator, okay, which we use a battery to start the generator. Once we start the generator, the battery comes in parallel to the generator, so that the battery gets charged, right? Okay, in that condition, generally the generator voltage will, if it's a 12 volt battery, the generator voltage will be slightly above 12 volt, which will be around say 14 volt. Okay, so if you will see that this battery is getting charged out here. So in this condition, you will have an 14 volt source connected in parallel to a 12 volt also, but again we are not violating any rule, because this is a practical circuit, and in practical circuit you will have an in a practical circuit we will have a series resistance, right? So if you see here, what happens is, this is 14 volt, this is 12 volt, and you will have 14 minus 12, which is 2 divided by 1.5, right? And which is the series resistance which comes in this circuit. So a small current is going to flow from the generator to the battery, so that will keep charging the battery. Is it okay?
Yes, sir.
Right? So in practical circuits, that is the same for your laptop chargers also, right? You are connecting a laptop charger, but you have a battery also running concurrently, right? So continuously. Now only thing to remember out here is what say this is 12 volt, can I have a 20 volt out here? Can I have a 20 volt out here? What will be the drawback? Okay, yeah, tell me. See, if you have a large, if the difference between these two is large, so a large amount of current will flow like this, right? And then I square R, so this resistance, internal resistance of the battery, okay, R into I square, okay, what is that is going to be generated? That is going to generate heat, right? Even in this case, it is going to generate heat. So your battery, if you have a lead acid battery, okay, the electrolyte will start getting heated up, right? Slowly. So it should be able to dissipate that kind of little bit of heat. But if you have a large voltage out here, then the electrolyte will start boiling, okay, or your battery might get spoiled. So generally these will be if you have a 12 volt battery, generally it will get charged, and although it's a 12 volt battery, it will get charged to around 13.5 volts. Then you will have 0.5 volt divided by the series resistance, a small current, and it is little bit of heating would happen in those batteries, but that is that is okay. And then you have a load also connected, so the majority of the current goes into the load from the source, whereas battery also, because this is at a higher voltage, most of the current will be given from the source and not from the battery. The charge in the battery will be preserved. So just to like if I were an industry chap, and I would like to ask this question: is it not possible to connect to voltage source, and does it ever happen in a circuit? So in textbooks, okay, the first part will always be explained, whereas the second part, we have a a tendency to skip these things. Okay, but in practical circuits you need to understand these kind of things also happen. Okay, is it okay with all of you? Yeah, so you got to understand this. There will be some heating out here. Okay, I square R heat, so that will heat up your battery. Okay, yeah, tell me. Somebody
Sorry, sir.
yeah, tell me.
By mistake, I've
Yeah,
touched
okay,
normal
no problem,
things.
no problem. Okay, so
Sir, you said that battery will get charged. How will it be charged? Like 13.5 volt?
uh, yeah, although the rated voltage is 12 volt, okay, a fully charged battery initially it will have slightly more than 12 volts. Okay.
Sir, how?
Okay, yeah. If you
It's
see the
making it 12.
lead acid batteries, okay, it is just that some extra bit of charges gets accumulated in those on those plates because of the external voltage which is applied.
So it creates new potential difference which adds up to it.
Yeah, yeah,
Okay.
something like that. Similarly, current sources also, ideally you can't have two current sources in series, okay, whose value are different. Okay, you can have only two current sources. I1 is equal to I2, that is permitted. I1 not equal to I2 is not permitted. But then you will see, like solar cells, you connect large number of solar cells. They are all current sources. They receive sun rays and they are all photovoltaic cells. They generate some amount of current. Okay, you can have them in series. So this photovoltaic cell is generating 2 amperes, whereas this is generating 5 amperes, but they are not ideal. So generally you have a parallel resistance. Here you will have a parallel diode. So this 5 amperes will come here, 2 amperes will go into this, and then you will have the rest of the 3 coming through this diode out here. So the net current available will be 5 amperes. Okay, so you can have two unequal current sources also connected in series out here. Right now, you will say what is the advantage? It is again the same advantage. If you have a single cell and if you have to draw 5 amperes, the terminal voltage required to be generated by this cell will be much higher. So when you have two of these cells connected like this, or n number of cells connected here, the terminal voltage for a particular load between these cells will be lesser. Right, if you have say 10 of these cells connected, the voltage across each of these cells will be lesser, because say RL is fixed to say 1 kilo ohms. So you have 5 amps, say RL is 1 ohm, so 5 volts. So if you have two cells connected, the voltage across each cell will be 2.5. Right, so that is how it will get divided. So that is the advantage in having current sources in series, and these are practical applications. So these things will be slightly different. Okay, now these we will learn subsequently, but I am just covering this slide out here just because in the tutorial, otherwise just based on power sources we will have very few problems. So I am just covering this aspect out here. We will discuss how this has come in the later classes, but just understand this formula so that it becomes easy in the Monday tutorial, where a power source with Vs and R is equivalent to an current source out here with an R in parallel. A voltage source in series resistance R is equivalent to a current source Is with R in parallel, only provided the value of Is should be Vs by R. Okay, you can either transform this to this or this to this. So only thing is you got to the Ohm's law kind of thing should be satisfied here. So this Vs, if you have ISR, you can represent this like this. Okay, and the value of Vs will be computed Is into R. Similarly, if you have this, you can transform it, you can represent it like this. So you just remember this particular slides. These are Thevenin and Norton equivalents. We will discuss the theory behind this later on. I just covered this slide out here to make your Monday tutorials and a little more interesting. Okay, so that's all for today's class. So we will next meet on Monday for the tutorials, and followed by the theory class on Monday. Okay, thanks a lot.